Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. This is for my Integrated Math 2 bunch looking at similarity of triangles. We are going to go over three theorems here. The angle-angle similarity theorem, side-side-side similarity, and side-angle-side similarity. If you've seen congruent triangle proofs and you've done some side-angle-side, angle-side-angle, things like that, this will probably hit home in a way that makes a little bit of sense to you. Basically, and we'll get into these, but what these mean are if you have certain parts of two triangles that you know are related to each other in a certain way, we can actually have that as enough information to say the triangles are similar. We don't have to know every part about them like we had to for, say, quadrilaterals or pentagons or some other shapes. Triangles are kind of special in that way we can do that. And we're going to see this diagram actually in the next shot. We're going to start with angle-angle. Now, in order to do that, let's first recall something here. Recall that if figures are similar, figures, any sort of figures you have, if we know figures are similar, then corresponding angles are congruent and corresponding sides are proportional. All right, now we'll get into those things once we determine we have similar figures. Now, if you have enough information to determine for yourself whether two triangles are similar, then the above two properties can be inferred because, of course, then you find out they're similar. But I say enough information because, again, for triangles, you don't need to know every bit of everything. Unlike other polygons, triangles don't need to prove every part to be congruent or proportional. I don't need all three angles congruent. I don't need all three sets of sides proportional. I only just need either two angles, three sides, or two sides in the angle in between as far as the statements here. Two angles congruent, three sides proportional, or two sides proportional in the angles in between congruent. Those criteria, those are the ones above right there. It'll still be critical for you to determine which parts correspond, though, because there will be triangles that face different directions, and they'll trick you in different ways, whether there's a rotation, a translation, a reflection, any sort of thing here. This one is just, both of these face the same way here, and we can actually make a good similarity statement here if we have enough to deduce that these two triangles right here, for example, are similar. And actually, they are, because if you look at this first one, guys, we're going to focus on angle-angle. Two triangles are similar to one another should they meet any of the following criteria. First one, angle-angle, says if two angles of one triangle are congruent to two angles of another triangle. Now, the interesting part here is it only says two angles here, right? If I write the angle-angle similarity, only two of them. Why don't we need the third? Well, because if two angles in a triangle are congruent, then the third have to be congruent. I don't know if you know that. That's also another theorem statement thing. Basically, all triangles add to 180. If these two add to the same amounts, then this is the rest of it that needs to add 180. So we don't need angle. You really only need two of them. And of course, if you find two, then the third one also kind of exists with it. Anyway, so a similarity statement I could make here, if angle A is congruent to angle X, and if angle B is congruent to angle Y, then C is congruent to Z, as we know. Triangle ABC here would be similar to triangle XYZ by the angle-angle similarity theorem. Sorry, I can't really draw that. By the angle-angle similarity theorem. Now, if that's the case, guys, what I was saying before was, of course, all other corresponding parts are either congruent or proportional. So I can go back to C and Z with these, and I could have done that without knowing they were kind of similar. And then segment AB is in proportion with segment XY in the same way that BC corresponds to YZ in proportionality, and XZ corresponds to AC. So I don't know if the squiggly lines kind of really help you with that, and we'll do more with these drawings within, but once again, the above two properties can be inferred if I have enough information, angle-angle being one of them, angle-angle being what I'm going to start with for these ones, in order to prove they're similar, and then use that information to find out missing information, mostly often side lengths through proportionality. So let's go ahead and get started. Now, not every problem is going to look like this, so obvious as in like, hey, I got my angles there. In fact, let's look at this first one here. Find the length of BE if possible. Now, the only possible way that we'll be able to find the length of BE in this problem is if we can determine that these two triangles are similar, and then if so, if we have enough information labeled from other side lengths to set up a proportion based on the similarity step. So what we have here, guys, and there's more than one way to do this angle-angle stuff. If I can find two sets of angles to be congruent, I am set. I could even find all three for you, and in this problem, I totally will, without even using that third angle theorem. Right here, guys, I have two angles congruent because these are vertical angles. ABC and DBE. Those are congruent because they're vertical angles there. If you notice these two lines that are parallel, guys, these two lines also cut by, say, a transversal right there. Sorry for the drawing. Gives me congruent alternate interior angles right here in angles A and D. So I have alternate interior angles there. I already have angle right here, as you can tell, guys. Angle A is congruent to angle D. And then angle ABC is congruent to angle DBE down there by vertical angles. And of course, guys, these are also alternate interior angles with C and E right here, because once again, a transversal for the two parallel lines. So I could have also done angle C congruent with angle E. What seems to be, I mean, this is by angle, I could do this, but I want to make a triangle similarity statement to get stuff started off, because I also still need to find out which parts correspond. That little hint down here, it'll still be critical for you to blah, blah, blah. This is super crucial, because there will be things that are messed up based on not knowing which parts correspond. And knowing which parts correspond really helps by making these angle congruent statements. A corresponds with D, C corresponds with E, and B, remember B was the vertex here, B must correspond in both of these together. Remember, B exists in both triangles. If these were two different triangles, you would see the letter B in both of them. So what's the triangle similarity statement I could say? I could call one of these triangles ABC, right? If I call one of them ABC right here, then what's the other one going to be? Well, A corresponds with D. If A is the first letter here, D is the first letter in the other one. And then B, because B corresponds with B in both of those. And then the last one is that E right there. So this is by angle, and I know that these two are similar. Awesome. Now, how does that help me find the length of BE? Well, let's still see if we can. They are similar. That's a good step one starting process. Now what we need to do is write a proportion for this problem here to determine what the length of BE is. And I'll start by doing it without actually writing out the numbers, because there's actually a little trick to this, guys. You see these two 54s, and you might assume that these parts correspond to each other because the numbers are the same. Actually, in a similarity problem, that's most often not going to be the case, because unless the triangles are congruent, corresponding sides shouldn't be congruent in a triangle. They should only grow in proportion to each other, which means one should be bigger than the other. The fact that these are 54 is either coincidence or something to throw you off. These two likely don't correspond. In fact, when we look at it, here's BC, here's BD. Does BC correspond with BD? No, because in triangle ABC, BC are the second and third letters, and in triangle DBE, B and D are the first two letters. So no, these parts don't correspond here. These definitely do not correspond. So, be very careful where you see something like those 54s. What I'd rather do is one of a couple things, and this is one of them, writing out the numbers right here to know what corresponds here. So I could see what BC should correspond to. Or do a redrawing of your triangles. And I've recommended this to my students before, and you really only need to redraw one of them, but I'll just do both just in case. So if I have ABC right here, let's just redraw DBE the same direction. I'm just going to draw another triangle. I'm going to call it DBE and put it the same direction in the corresponding parts right next to each other. A is D, B is B, C is E as far as correspondence. And this helps because now when I write the numbers that make segments that match them, like AB is 36, DB is 54, see that? DB is 54, BC is 54 here, BE right here is unknown, and then these two are completely unknown as well, but we need to find BE. This shows what parts actually truly correspond to sides. AB and DB correspond right here. AB is to DB as BC is to BE. BC is to BE right there. You could tell those parts correspond when they're drawn the same direction. Basically, DBE is rotated from maybe 180 degrees the wrong way, right? So we need to rotate it the right way to see if they correspond. You don't need to redraw, but I am giving you the situation that shows these 54s did not correspond. 36 corresponded to 54. 54 corresponds to the unknown. So what is this again? BC over BE right there. Let's see if that makes sense without even the redraw. Could have I used this here? AB, first two letters. DB, first two letters. They correspond. That works out. BC, second two letters. Second and third letters. BE, second and third letters. See, those correspond. So I wrote a proportion out either based on the numbers or the drawings. And this is one of those things, guys, I'm not going to do both of them every single time. And I'm obviously not going to re-explain this every single time here. But let's go ahead and write that thing out. AB is 36. DB is 54. And BC is 54. And BE is some unknown we're going to try and find. Okay? So let's go ahead and solve this one based off this. And guys, I have numerous examples here, so I am going to try and speed up through these afterward. I just want to get this explanation in to really make sure that the corresponding parts made a lot of sense, because this is my first video hitting you guys with this. Now, cross multiplication is a total option here. I'm going to utilize that option, but first, please reduce a fraction whenever you can. There are a lot of different ways we can reduce fractions. I know some of them will be a little confusing. I'm just trying to save face and time, even for myself. I don't have a calculator in front of me. 36 over 54, I know reduces to 2/3 because I can divide those by 8. There's also a small thing here, guys. I can divide both sides by 2. The 2 on top here, I can divide 54 by 2. So if I divide these by 2, I'll get 1/3 equals 27 over BE. And if I cross multiply there, I'll get BE equals 81. Again, I'm saving time for the algebra. I want you to make sense of the geometry. Obviously, proportionality is kind of a new thing for some people. The cross multiplication step I did was BE times 1 and 3 times 27. And I got BE equals 81. So the unknown length here is 81. And that's what keeps this thing in proportion. Basically, this triangle is 2/3 the size of this triangle, and 81 is 2/3 the size of, 54 is 2/3 the size of 81, just as 36 was 2/3 the size of 54. So that's how the triangles work, guys. That's the drawing. There it is. Let's keep going. Let's do another angle 1, or see if we can, through angle, find RT if possible. Now, RT is this entire length right here. And this one's kind of messy because there are two triangles, but you really got to see them for what they are. This one would be helpful to redraw them as two separate triangles. There's something I will use with these two triangles together in a sec. I'll show you what it is. But first I'm going to redraw these as two separate triangles, guys. There's a smaller triangle here that's RSV. You can probably clearly see that from this drawing here. RSV, there's some congruent angle with another angle in the other triangle, and I got an 8 and 10 right there. Now, can you see the other triangle here, guys? RTU. See that bigger one right there? That's RTU. RTU. Now, T was congruent to S right there. You can kind of tell what seems to correspond based on what's there and based on the rest of the drawing. I think that seems to make sense. Now, I have a length 12 here, but that's the only information that we have after that. I don't know anything about RU. I don't know anything about RT. And you know what's interesting, though? We could find out what RT was if we found out what ST was right here, but I think we could just figure out what all of RT is if we get a proportionality set up, right? This is the unknown. So if we can prove these two triangles are similar, then we can go ahead and do that. So how do we do that? We have one set of angles right here, congruent. Now, you're going to learn something called side angle side soon that you're going to be able to use. We can't use it here, though, because we don't have both sets of sides proportional, because we don't know what RT is. We do want to see if we can find another angle congruent here. And there are two different ways that we can do it once again. Here's way number 1. If you look at the original triangle, the original drawing, excuse me, this angle R was shared. It was shared in both triangles. As you can tell, there was a big triangle here. Notice that angle R. And there's a small triangle here. Notice that angle R. Because it's shared, it is congruent to itself. This is something called the reflexive property, when an angle is congruent to itself here. Now, you have to be careful because there was a B that was shared, sort of. It was the same letter in both triangles here, and it actually happened to be congruent to itself because they were vertical angles, but it wasn't shared in the same way. Right? It wasn't literally the same angle used twice. These are two different angles here that were congruent. This was actually literally a shared angle. So just because it's the same letter doesn't always mean it's shared. Because it's shared, it means it's shared, and that's what those case here. So check it out, guys. I have angle there. I could have figured it out like that. Here's the second way of finding these two angles, and this one's a little bit trickier. Let's say I didn't know that, or I couldn't figure this one out. Let's say I didn't know it was shared. Because these two angles are congruent here, guys, this is two lines cut by a transversal, and because these two angles are congruent, they're corresponding angles. When corresponding angles are congruent, lines are parallel. So these lines are actually now parallel. And you know what that means? When two parallel lines are cut by a transversal, guess what? These are corresponding angles right here. And corresponding angles are congruent when lines are parallel. So that's another way I could have found out that V was congruent to U. So I only really needed two of them. I found all three. I'm just giving you ways that you can do it based on the problem. But I can say, and here's where I got to make my triangle similarity statement. Make sure I have parts that correspond. Thankfully, they're drawn the same way. But triangle RSV is similar to triangle RTU by angle, angle. Okay, so by angle, angle there. There they are. So let's go ahead and solve for RT, the unknown based on proportionality. Once again, whether you do letter order or drawing diagram, whatever it is up to you. I have RS. I have this long side in this triangle matched up with this unknown side RT. RS is to RT as this shorter side here, 8, is to 12 here. SV is to TU. So let me write that out with the numbers. And I think once again, I'll be speeding up faster with this. And, there's actually a third way to do all this triangle stuff that I'm talking about. And it really does have to do with side lengths. And I think I'm going to do it probably for the next sets of problems if we have an opportunity to really talk about them. Maybe I can talk about it with these ones. Maybe it'll help to talk about these ones. Okay, before I do any cross multiplication stuff, just to kind of save face and save time here, 8/12 reduces once again to 2/3 like that last one. 10 over RT equals 2/3. Cross multiplication wouldn't be a bad thing here. Maybe I'll just set it up right now. But if I cross multiply, I'm going to have 3 times 10 and 2 times this unknown RT. So this will say 30, that's 3 times 10, equals 2 times RT. Divide both sides by 2, I'll get RT equals 15. And that is the length of all of RT right there. That is 15 units long. That means that little guy is 5 units long, if that matters to you. Okay, the last thing that I want to say before I kind of move on was, when you do the proportionality, what will make sense if you don't consider doing the redraw or something about corresponding parts, what would make sense is that in corresponding parts, if these two triangles are similar, there is no reason that I should ever... You know what? I'll save it. I'll do it when we do the side angle side stuff because I'm already at 17 minutes. All right, so I have one more angle here, and yeah, guys, this thing can run through a bunch of examples here. One more angle thing to set up. I have 2 sets of angles congruent here, P and T. Can I get any other sets of angles congruent? Well, I have a linear pair right here, and I have a right angle right here. So this tells me that this is also a right angle, right? 2 right angles are supplement a linear pair. So I have angles congruent there. So yeah, I got an angle here. Angle. These two triangles are definitely similar. So I can go ahead and say that triangle, let's call this TSQ, triangle TSQ is similar to triangle, which one? T corresponds with P, right? Because those are the congruent angles. So P, this one also has an S, and that's the right angle, just like that one is, S and then R. Once again, by angle. Let's find the length of all of PQ if possible. PQ is just this thing right here, okay? Now, what's going to help? What's likely going to help here, once again, whether you consider redraw or otherwise, what's likely going to help here is finding all of PS and maybe part of QS and things like that, right? We gotta work some things out here. And we have some proportionality things to consider as well. When it comes to corresponding parts, guys, 9 is like the hypotenuse of this right triangle. I don't have that number. 15 is the long leg of this right triangle, right? TS is with PS, right? But I don't have any information on PS. 12 doesn't correspond with the 15 or the 9. So I'm missing bits of information in these triangles here. And again, a redraw, guys, the redraws really do help. I'm going to draw both these kind of up right here, where I got 15 and 9 in this TSQ. And then, of course, the bigger one right here, I have PSR. And you can see that this 12 does not correspond with the 15 or the 9. If you could see the 12. There we go. Whoa. So, what do we do? This is where you can use if, remember, it says if possible. Now, I'm leaning on it is possible as far as going through this problem. We got to look at Pythagorean Theorem. We can find out what SQ is through Pythagorean Theorem. Oh, you know what? When I'm looking at this problem, actually, I don't know if this problem actually makes sense now that I look at it. And, I didn't set up this problem. So this problem is defunct by nature. And honestly, I almost feel like rearranging some of the stuff to actually make it work. I don't know if it's worth our time to do that. For the sake of it, I guess I'll say it's not. Here's what I was going to say, guys. Pythagorean Theorem, I could find out this missing side to start off with, right? The problem is the hypotenuse is shorter than the leg, and that's impossible. We'd get a negative length there. There's something wrong with the drawing of this triangle here, and this was from a textbook. I don't know if they meant to do this, but honestly, yeah, if we figured out this length here, which would have been really nice, if we figured this length out, we could then use that and then set up proportionality right here to figure out this length. And then we could have used that and cut out the unknown side there. Again, I really wish that this thing was already set up the way that it was. Maybe if I swapped the 15 and 9, but I don't know if it's worth the time. Let's go ahead and move on. Let's say that this was not possible. And again, the reason is not because, we couldn't manufacture it the way we wanted to. It's because the hypotenuse is for some reason a shorter length than its leg. That's really the only reason. If these were swapped, it's possible. But I'm on 21 minutes, so let's keep going. We've done some angles. Okay, so there's your angle stuff right there. Now let's look at side, and side, angle, side. Okay, determine whether the given triangles are similar. Now what we have are two different triangles with all sides set up here, and we have no known angles marked. This is where we're going to look at side, and it's basically all proportionality tests. Now, just like we did with other shapes and objects, we tested the proportionality of these, and we had to see if all sides were proportional. On top of that, we had to see that all angles are congruent. With triangles, if you find out all three sides are proportional, you're good. Triangles are similar. So here's where I wanted to say the other thing that I did want to say here. I might not have to redraw these objects so they face the same direction as long as I know which parts should be tested to correspond with based on their lengths in comparison to the lengths in the triangle, to the comparison to the other lengths in the triangle. What I mean by that is, let's look at these lengths here. 4 is the smallest length in this triangle, then 8, then 10. In this triangle, I have 6 as the smallest, and then 12, and then 15. If I am to do a test of similarity here, there is no reason that I should not be testing smallest side with smallest side, medium side with medium side, and longest side with longest side. Regardless of drawing, there's no reason I should not be testing that. That's the only way that similarity would even be possible. So when I test this, and I'm not going to write out all the letters, I'm just going to do the numbers straight up, guys. I'm going to test and see how 6 divided by 4 matches up against 12 divided by 8 and 15 divided by 10. Now, I do want you to see what I did happen to do besides small, medium, and large comparing sides, is I did go from the big triangle to the small triangle each time here. Now, you could have also done it the other way. You could have gone small to big. You could have said 4 over 6 equals 8 over 12 equals 10 over 15. It doesn't matter which way. You'll get some ratio either from small to large or large to small, but you have to stick to the same direction each time you go. And also, once again, I did do smallest side to smallest side, medium side to medium side, and largest side to largest side. Now, as we reduce these fractions, 6/4 reduces to 3/2, 12/8 reduces to 3/2, 15/10 reduces to 3/2. These all share the same similarity ratio. Because of this, these two triangles are similar. By side. This is your proportionality test for side. So let's go and make a similarity statement. Now, make sure you do the parts that correspond. How about we go from one vertex across the smallest side and then across the medium side there. So I'll do triangle NLM. NLM is similar to triangle. Let's go from that J across the smallest side and then the medium side, JGH. JGH. By side. So they are similar indeed, based on that test there. When you do letter stuff, the first order that you do for things doesn't matter. The second one should just follow in correspondence. What I tend to do, guys, I tend to go alphabetical, the first one, and then I just follow with whatever the next one is. Okay, let's try this one here. Now, there are two different triangles. Hopefully, we can kind of break apart what this thing kind of shows here. This is where, once again, a redraw really may help you. I have M, N, and P, 4, 6, and 8. And here I have, this is the part that, once again, what should line up here? this is 8 plus 4. That's 12. 8 plus 4 is 12. So MQ is 12. And that would be the longest side among these three sides in this bigger triangle MRQ here. So it should also line up with this bottom one here. If I did a redraw, 12 would be on the bottom there. And then the shortest side should be here. So I'm going to make that the 6. And then this one can be the 10 right there. So if parts correspond, again, you don't have to redraw it that way. I'm just kind of giving you the whole, if you want to compare it. So M goes to R 6 units away, goes to Q over there. All right, so let's go ahead and do a similarity ratio test and see if this works. We're going to do small to small, medium to medium, or sorry, medium to medium, large to large. So let's go and check out 4 over 6 equals 6 over 10 equals 8 over 12. All these have to be equal for this thing to be in proportion with one another. So 4 6 is 2/3, 6 tenths. Ooh, look at that. That's 3/5. That's different. And then 8 twelfths also is 2/3. 3/5 is not equal to 2/3 with these ones here. This one clearly breaks in such a way that these triangles are not similar. There is no side-side-side similarity. You don't need to make a similarity statement of MNP is not similar to or anything like that. They're just straight up. You can just straight up say not similar here. And that math kind of adds that up. Kind of shows that. All right, those are two side-side-side scenarios, guys. You're doing proportionality tests based on, once again, the sizes of the sides, and small should always go with small, medium with medium, large with large. Now let's check out side angle side similarity theorem. Same kind of stuff, guys, but in side angle side, we really have to understand that the angle known has to be in between the two sides. When it says the included angles, it means the angle made by the sides that which we're measuring, that which are labeled, that which we are testing for proportionality. So when we look at these two right here, guys, straight up, even if these sides do have proportionality to them when you just compare things such as, and you know, these things do correspond in such a way that I have congruent angles here, A and F, and then this 10 is the longer side, like 5 is here, so I can check 10 over 5 against this next short side that comes there, 6 over 3, and you do get 2 equals 2. That does check out. Also, you get that these two angles are congruent. The problem is this angle is not marked congruent in between the two sides that we marked proportional. This is not side angle side right here. This is not SAS. This is ass. This goes from angle to side, angle to side. If you want side angle side, you're going to need this angle known to be congruent to this angle somehow. Side angle side with side angle side. You need the one in between. And I have no information that can conclude for sure that these two triangles are similar. Now, do I say not similar? Well, I don't know if they're similar or not. In fact, this proportionality shows that they actually might be. But I don't have enough information. All I have is I don't have enough information. In this case, there are sometimes where we say not similar. These two guys, in the previous one, these two were not similar. Similarity ratio did not apply. These were not similar. Here, similarity ratio applied, and here I had two congruent angles that corresponded. But this one's not enough info. I don't have enough info here because I don't have a way of determining either whether these two sides are proportional or whether these two angles are congruent. I just don't have enough info, guys. I have one more for you. And hopefully, now as you look at this, you're going, oh, angle side side, it's ass again. The difference is this is a right triangle. And in a right triangle, you can determine the third side of a right triangle if you know the other two sides using, this time we get to use Pythagorean Theorem. So if I use Pythagorean Theorem to figure out the third side, and Pythagorean Theorem to figure out the third side, then perhaps we can do a proportionality test alongside. We also know that two angles are congruent because they're right angles. Maybe, just maybe, we can use side angle side here. So in terms of figuring out this length NO, I don't know what that is yet, so let's find out. When we square NO with 8, we 10 squared with 8 squared, I mean, we get 10 squared. NO squared plus 64. Oh, this is a long video, sorry guys. Equals 100. NO squared equals 36. Take the square root. NO equals 6. That's the length of NO. So this length right here is 6. Now this GH right here, GH squared plus 3 squared. Notice that I'm using the leg. This GH is a leg, so GH has to be squared plus 3 squared equals 5 squared. GH squared plus 9 equals 25. GH squared equals 16. Take the square root, you get GH equals 4. So this length right here is 4. All right. Now we have enough information to conclude whether or not they are similar. We don't know whether they are, but we have enough information to make a decision. We can do this one of two ways, guys. We can either do side, 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 because now we have all three sets of sides, or we can do side, angle, side. Either they'll both work or they won't, as long as the problem that's set up works out. Unfortunately, we had a problem right here that I should have double checked before. So stupidly. They set up hypotenuse larger than. I really wanted them to swap. It would have been a nice problem to do. But you know what? We have another problem that we're doing Pythagorean Theorem with, so it's totally cool. I'm going to do side, angle, side because that's kind of the thing that we're on. If you want to test all side, side, side things, you can. But side, angle, side means I should be testing the two sides that make, whoops, not that one, the two sides that make the congruent angle that we know. So 10 and 5, I'm not going to bother testing. I could, but I'm not going to bother testing. Side, angle, side with side, angle, side. Now, which parts correspond? Test long leg with long leg with long leg against short leg with short leg, right? So 6 does not correspond with 4. Just because they're both on the bottom, this thing is toppled over. This thing is rotated downward. The 6 corresponds with 3. 6 and 3 are the shorter legs of this right triangle here. So I can do a 6 divided by 3 right there. I'm not redrawing. I do 6 divided by 3, and then 8 divided by 4, because those are the longer legs of their respective triangles. I'm saying legs, not the hypotenuses right there. So 8 divided by 4. Short with short, long with long. And 6 over 3 is 2. 8 over 4 is 2. 2 equals 2. That seems to check out. We also know that angle N is congruent to angle H. That's marked. They're right angles. And we use Pythagorean Theorem to figure out the other corresponding parts there. We have, guys, side, angle, side with side, angle, side. Two sets of sides that are in proportion with one another, the 8, 6 and the 3, 4, and the angles in between that are congruent there. By the way, guys, if I did do 10 over 5, oh, that equals another 2. We also have side, 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 but I'm going to go ahead and do the other one. Let's do this in alphabetical order. MNO, triangle MNO is similar to triangle, okay, what corresponds? From M to N is the long leg. Where's the long leg here? G to H. G to the right angle. G to H, and then to J there. So that should correspond there by side, angle, side. All right, that was over a half hour's worth of stuff. I actually did not intend for that to happen, but a lot of the proportionality stuff is things that people are having trouble with right now. And I really want to make sure that I cover all the different kinds of problems that you are likely to see on this thing. So in just concluding, we check all those things off. They're there. So thank you so much for watching, guys. Again, apologies for the longer video at play, but I do hope that that really helps solidify some of the things you're looking for, provided that I didn't go too fast in the algebra for you to not know how to do that already. All right. Thank you much. Take care.